Today we're going to talk about prime factorization and the greatest common factor with regard to polynomials. So let's remember what we know about prime factorization and factors of numbers. For instance, we can list the factors of 48. The easiest way to do these is in pairs, 1 and 48. And then 2 divides evenly into 48 as well. It goes 24 times. 3 divides evenly into 48, 16 times. 4 goes 12 times. And 5 doesn't go into 48, but 6 goes in 8 times. 7 doesn't go in, and now we know that we've listed all the prime factors because the next one would be 8, which we've already listed. So those are all the factors of 48. Now let's list all the factors of 36. Again, in pairs is the easiest way, 1 and 36. And then 2 divides evenly into 48 into 36, 18 times. 3 goes 12 times. 4 goes 9 times. And then 6 goes 6 times, and we're done. So now the greatest common factor would be those factors that those two numbers have in common, but the largest one of those. So the largest number that those two factor lists have in common appears to be 12. So the greatest common factor of 48 and 36 is 12. So now we're going to write the prime factorizations of 48, 36, and then the GCF as well. So in order to do those, we're going to make factor trees. 48 is divisible by 6. It goes 8 times. If I continue until I get prime factors, 2 and 3 are prime factors. 8 divides into 2 times 4. 2 is a prime factor, so we'll stop there. And then 4 divides into 2 times 2. So all of the prime factors together are 2 to the 4th times 3. And remember, there's an understood first power on that 3. Okay, so let's make a factor tree for 36. 36 divides into 9 and 4, neither of which are prime factors. 9 is 3 times 3. Both of those are prime factors. And 4 is 2 times 2. Both of those are prime factors. So the prime factorization for 36 is 2 squared times 3 raised to the second power. Now let's take the greatest common factor, 12, that we found, and let's write a prime factorization of it. 12 factors into 4 times 3. 3 is a prime factor, so that'll stop there. 4 can factor again into 2 times 2. So now we have all the prime factors of 12, which are 2 squared times 3. And remember, there's that understood exponent of 1 on that 3. What you'll notice about the prime factorizations is that the GCF has both factors common to 48 and 36. Raised to the lower of the two exponents in their prime factorizations. What that means is, if we look at the factors of 2, the greatest common factor has the lower of the two exponentiations for 2. So 48 has a factor of 2 to the 4th. 36 has a factor of 2 squared. So the greatest common factor has a factor of 2 squared, the lower of those two exponents. Now if we look at the factors of 3, The two prime factorizations of 48 and 36 have 3 to the first power and 3 to the second power, so the GCF has 3 to the first power. Okay, so let's use what we've learned to write the greatest common factor of some monomial expressions. So think of A as a prime factorization. So we're going to look at the factors of A, and we're going to pick the lower of those two exponentiations. So the GCF for those two monomials in A would have a factor of A to the second power, the lower of the two exponents, and a factor of B to the second power, the lower of those two exponents where B is concerned, and then C raised to the first power, the lower of those two exponents. In B, we have a numerical and a variable factor part to each of the monomial expressions. So we'll want to write the greatest common factor of 14 and 21. 14 and 21 are both divisible by 7. That's the greatest common factor of both of those. Now we'll list the factors of A. Each factorization has a factor of 1A, so we'll leave that as A to the 1 in the GCF. And then factors of B, the lower of the two exponents is B squared. And then for factors of C, the lower of the two exponents is C cubed. Okay. In the next factorization, the greatest common factor of 2 and 10 is 2. And you'll notice that the first factorization has a factor of A, but the second does not. The greatest common factor will not have A in it because A is not common to both factorizations. And then the lower of the two exponentiations for the B's is B raised to the third power. And let's try the last one. This one has 3 expressions. The greatest common factor for 4, 6, and 7 is 1. So we're not going to write a numerical coefficient since the 1 is understood. And then the lower of the exponents for A is A raised to the first power, and the lowest of the exponents for B is B raised to the second power. So that's all that all 3 of those have in common. Okay, let's take a look at possible pairs of factors of 40. And then we're going to look for one that has a given sum. So possible pairs are 1 and 40. It's always easiest to start with 1 and the number, and then 2 and 20. 3 doesn't divide into 40. 4 goes in 10 times. 5 goes in 8 times. 6 doesn't go into 40, neither does 7. Since we've already listed 8, we're done with our factor list. Now we're going to circle the one that has a sum or adds up to 13. That would be 5 and 8. All right, let's list factors of negative 24. Since this number is negative, remember that you have to have factors that where one is negative and one is positive. So I can start again with 1 and the number, negative 24, 2 and negative 12, 3 and negative 8, 4 and negative 6, 5 doesn't divide evenly, and then we could say 6 and negative 4, 8 and negative 3, 12 and negative 2, and 24 and negative 1. It seems like the last 4 that we listed are repeats, but the negative signs are reversed. So that makes them different pairs of factor. Now these two have to have a sum of negative 8. And it looks like they don't. So we're going to write not possible. since 1 and negative 24 add up to negative 23, 2 and negative 12 add up to negative 10, 3 and negative 8 add up to negative 5, 4 and negative 6 add up to negative 2, 6 and negative 4 add up to positive 2, 8 and negative 3 add up to positive 5, 12 and negative 2 add up to positive 10, 24 and negative 1 add up to 23. So this one was not possible. That's going to happen every now and again. Next one, factors of 45 with a sum of negative 18. Now we can narrow this down just a little bit. If I know that their sum is negative 18, that means that both of the factors have to be negative. So negative 1 and negative 45. 2 doesn't divide evenly. Negative 3 and negative 15. 4 doesn't divide evenly. Negative 5 and negative 9. 6 doesn't divide evenly. 7 doesn't divide evenly. 8 doesn't divide evenly. And now we're back to 9. So that looks like our complete factored list. And negative 3 and negative 15 are the pair that add up to negative 18. If we want to find a missing factor, what we need to do is divide. Just the same as if we had 2 times x is equal to 10, in order to find that missing factor of x, we would divide both sides by 2 in order to find the missing factor. So we're going to do the same thing right here. In order to find out what goes in that blank, we'll do a division, and that division will be 18c to the 6th divided by negative 6c raised to the 4th power. That division gives us negative 3c raised to the 2nd power. In order to find out what goes into the next blank, we'll do a division of 16x to the 4th y to the 3rd power divided by 8x squared y, and that division will give us 2x squared y squared. Now, we're going to use the distributive property to do some factoring as well. We think of the distributive property as a way to multiply. A times the quantity b plus 2 is ab plus 2a if we distribute the a into the parentheses, but we can also use it to factor or undistribute. In this polynomial right here, it looks as if both terms have a common factor of x, so that factor can be undistributed and then written as x times the quantity y plus 5.